start by thanking Natasha, Sergei, and all the organizers for the invitation. I hear Natasha arriving. Thank you. It's a very beautiful place and always a pleasure to be here. So I will talk about nickelate-based superlattices and some recent work we performed in Geneva. But following the instructions of Natasha, I will have a first long part, which is where I will introduce some elements and concepts which are necessary to understand the recent results we obtained in Geneva. And also, we had already on Tuesday and Wednesday very nice talks, and some of these talks have mentioned a few things that I will need. So there will be some overlap between this presentation and some of the previous talks, but it's probably not a drama. So I will talk about metal-insulator transition systems, in particular the nickelates. And the characteristic feature is that these materials are, here you see the resistance versus temperature. These materials are in general metallic at high temperature, and at some temperature they transition into an insulating state. The category of materials or the family of materials I will discuss are transition metal oxide perovskites, and it was mentioned yesterday very nicely in your talk. With the formula AbO3, so the structure is quite simple. You see this cube. The A cation is at the corner of the cubes. The B transition metal is in the center, and you have this oxygen octahedra around. And the name comes from the discovery of calcium titanate. And it's important to know that it's a very common structure on Earth. Now, why we're interested into these transition metal perovskites? Because these metals display a variety of properties depending on the choice you make for the A and B cations. They can be insulating, they can be conducting, but also they display very many instabilities. Some are structural, I will come back to this in a minute, and some other are electronic. So you see that in this family of materials, you find dielectric or paraelectric insulator like calcium titanate, strontium titanate, but you find ferroelectric materials like barium titanate or lead titanate. You see also systems which display orbital order, magnetism or superconductivity, and all these properties are found in the same family of compounds with the same crystalline structure. Additionally, many of these materials have rather similar lattice parameters. You see an example with lead titanate, which is a rather famous ferroelectric material. You see that in plane, the lattice parameter is 3.904 angstrom. You compare to strontium titanate, which is paraelectric, 3905. So these unit cells are rather similar, and so it's a little bit like Lego bricks, and it allows us to realize rather perfect structures today using different techniques. And you see here one example of a film which has been grown on a substrate, and in view of the quality of the material, you need to put this yellow line to indicate the interface between the substrate and the film. Now, why do we do this? Because we would like to find ideally novel properties or novel functionalities, and these novel properties can come of the heterostructuring itself, because you can combine different materials in a heterostructure, but they can also come from interfacial couplings that can occur at oxide interfaces, and this field has been sometimes named oxide interface physics. So we heard yesterday already about, on Tuesday we had a very nice talk on metal insulator transition in vanadates, V2O3. Here this is an example of metal insulator transition in VO2. So the system is transitioning close to room temperature to the insulating state, and along with the transition, you have a structural transition from a rutile phase to a monoclinic phase. The system I will discuss in great detail later is the metal-insulator transition in nickelates. So you see here one example, neodymium nickelate, resistivity versus temperature, metallic, transition to an insulating state. And also in this system, and you will see that it is very important, there is, along with the metal to insulator transition, a structural transition, and the material turns, and that was mentioned by Andrea yesterday, is metallic and orthorhombic at high temperature, but there is a phase transition, a structural phase transition, and the system develops a breathing mode and becomes insulating and monoclinic at low temperature. Why do we study these materials, and in particular the nickelates? If you go to this publication, you will see here that there are quite many applications which are possible with these materials. I will not list all of them, but we heard 2 days ago, we heard a talk about resistive switching using these nickelates as possible elements for neuromorphic computing. And I wanted to mention that recently in Geneva, we use a nickelate film. You see here the device. This is a substrate, lanthanum aluminate, a nickelate film. And depending on the choice you make for the electrodes, you can get volatile or non-volatile resistive switching on the same platform. And this could be eventually an interesting system to pursue for possible applications. The outline of the talk, so 2 parts. In the first part, I will discuss metal-insulator transition and nickelates. So I will try to introduce things which are important to know or to understand, sometimes very briefly. I'll give some examples of MITs, and then I'll focus on the nickelate family, giving the basic properties and the phase diagram of the system. Then I'll discuss the electronic structure and the origin of the transition. And the second part will be about recent work in Geneva, where we have combined different nickelate compounds in heterostructures and studied the behavior. And the first thing I will discuss are superlattices made of 2 different nickelates, and you will see that there is a special type of coupling of the metal-insulator transition at short wavelengths. And then I'll show you how one can play with this coupling, and finally I'll use this special coupling to show you that one can turn a metallic layer into an insulator. So things to know and to understand. First, let me mention the structural instabilities of the perovskite structure. So when you look at the perovskite structure in the cubic phase, you realize that ideally you would like that the ionic radius of the A cation plus the one of oxygen is square root of 2 times the ionic radius of the B cation plus oxygen. And the ratio between these two is called T. This is a tolerance factor or Goldschmidt tolerance factor. Now, if T equal 1, the structure is a simple cubic structure. But now, depending on the choice you make for these A and B cations, this ratio is not 1. And what happens is that if T is larger than 1, the B cation has too much space. And so often what happens is this cation goes off-center, and sometimes you get tetragonal phase and ferroelectricity. If T is smaller than 1, as here, and that will be the case for the nickelates, the B cation is too big. And what happens is that the oxygen octahedra rotate to accommodate for this difference in size, and often in perovskite you go to an orthorhombic phase. And this is what you were seeing in this phase diagram of in this picture before. For some of these materials, like calcium titanate and strontium titanate, the ground state of the system is a distorted state where the octahedra rotate. And for lead titanate, or barium titanate here, this tolerance factor, which is smaller than 1, is producing a polar instability and leads to the ferroelectric state. Now, it's important to know how to describe this rotation, these rotations, and there is a rather nice way to describe this rotation. This is what is called the Glaser notation, quite easy to understand. The Glaser notation uses 3 letters, A, B, C, And these letters describe the rotations around the three pseudocubic axes. So A along the x-axis, B along the y-axis, and C along the z-axis. The letter is linked to the amplitude of the rotations. So if you have two times the same letter, it means at the same amplitude of rotation. If you see a plus, it means that the rotations are in phase. If you have a minus, it's out of phase, and 0, no rotation. So for instance, strontium titanate is cubic at room temperature, so A0, 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 no rotation. But at low temperature, below around 100 or 110 K, you develop a rotation, an anti-phase rotation in one of the direction, and so at low temperature, it's A0, A0, C minus. Now, the nickelates, which will be the subject of the talk, are orthorhombic. And in an orthorhombic structure, you have three different rotations, which are indicated here, A minus, B plus, C minus. So you have two directions. You have anti-phase rotations, and in one direction, you have in-phase rotation in this PNMA description. This is one example of an orthorhombic structure, lanthanum vanadate. So you see here the orthorhombic structure. And if you look at the orthorhombic lattice parameters, you see that the B-axis, the axis which has the in-phase rotations, is longer. It's called the orthorhombic long axis. And what one should simply remember is that along this axis, you have in-phase rotations. And you have a relation here between the orthorhombic and the pseudocubic lattice parameters. Important is that coupled to these rotations, we have an antipolar instability, an antipolar motion, and this is what I would like to discuss with you. The three rotations induce or couple to a mode which is called x5 minus, which is here, through this term, phi xy, phi z, x5 minus. And this antipolar motion is a displacement of the A cations in the 1,1,0 pseudocubic direction. And this is what you see here in this compound, strontium TiO3. You see that in the orthorhombic phase, you have this plane of strontium cations which move in this direction, but the next unit cell, they move in the other direction. So an antipolar motion, and you can show or you can calculate, and this is what you see here, the polarization induced by this antipolar motion, and you see that it goes here from plus maybe 8 microcoulomb per square centimeter to minus 8 microcoulomb per square centimeter. No net polarization because it's antipolar. But this has been studied because there has been a proposition by James Rondinelli and Craig Fenney that one could use eventually this antipolar motion to realize artificial ferroelectric material. And the idea is shown here. If you grow superlattices with two perovskite, ABO3, A prime BO3, and you realize odd superlattices, for instance, one unit cell, one unit cell, one unit cell, you see that now in this stannate structure, where you have strontium here and barium here, so it's strontium TiO3, barium TiO3, you see that you will have a displacement of the cations in this direction, the strontium, but the next plane is barium. The displacement will be different, the Born effective charge will be different, and eventually you develop a net polarization. And there has been some work in this direction. And I will mention a little later in the talk that it can be interesting to measure this antipolar motion. And if you do scanning transmission electron microscopy and you look at the lattice, and if you have good eyes, you can see directly the zigzag of the A cations. But there is a technique which allows this displacement to be observed. It's an adapted geometrical phase analysis, which in general is used to determine strain. But if you use this technique, and this is what you see here, you can beautifully see the displacements. So red and blue indicate displacement of the A cations in different directions. And when you see this, you know that the long axis, the orthorhombic long axis, is perpendicular to this displacement. Okay, metal insulator transition, a few words. Different things have already been mentioned on Tuesday and Wednesday. Let me just remind you that if you follow, if you study band theory and if you have a periodic crystal, you know that you open a gap at the zone boundary. And now if you have 2 electrons per cell, you have a filled band and it's an insulator. Now in general, if you have a partially filled band, you have a metallic state, but we know also, and it was mentioned, that sometimes for half-filled systems, you find an insulating state. And it was mentioned that, for instance, in 1D, if you have a 1D chain with 1 electron per site, you have a half-filled system, but we know that in 1D you have the spiral's instability, and the lattice goes through a distortion, form dimers, and then you double the unit cell. By doubling the unit cell, you now open a gap at, say, the previously half-filled band, and your system is turning into an insulating state. Was also mentioned, I think several times, the important mode transition. It will be important here. So this is now a site model. In 2D, we have 1 electron per site. And one has to consider the bandwidth of the system, which is linked to the hopping, and the on-site Coulomb repulsion U, the price you pay to have 2 electrons on the same site. And I think you saw this already yesterday or on Tuesday. If you trace here the density of states as a function of energy, if the on-site repulsion is very small, you have the classical band picture. You have a half-filled band. The system is metallic. But if you're switching on the interaction, or if you reduce the bandwidth, at some point your system is turning into a mode insulator with this mode gap that you see here. And there is this beautiful experiment which was realized on strontium vanadate film. Strontium vanadate is a cubic metal. And you see here ARPES photoemission, where you see here the spectra for thick films, 100 unit cell, and going down in thickness down to the monolayer. And by doing so, changing the dimensionality, eventually the bandwidth of the system, you see that you have a picture which resembles very much to what I showed you before with the opening of a gap for these very, very thin layers. If you trace the mode insulating state as a function of here filling, so here it's half filling, and U over W, you see that you develop this mode insulating state in this gray region. And you see here that you can access or leave the mode insulating state by changing the bandwidth or the interaction, but you can also leave the mode insulating state by changing the doping. And this is the idea which is behind the mode transistor. One more thing to mention is the difference between mode insulators and charge transfer insulators. Now this is the role of the oxygen P band. And the distance in energy between the D band of the transition metal and the P band of the oxygen, delta, is called the charge transfer gap. And you have 2 situations, or 2 extreme situations. The first one is here, when your oxygen P band is way below the D band of the transition metal, and you open, you switch on interaction and you go to the mode insulating state. The gap is between the 2 parts of the D band, and this gap is U, and this is a motorboard insulator. But if the oxygen P band is very close to the D band, like in this case, and this is a case of the nickelates, when you open the gap which will be which will be relevant will be the charge transfer gap between this upper part of the D band and the oxygen P band. And this is discussed in this famous paper of Zahn and Savatsky and Allen. Okay, let me now discuss the electronic structure in perovskite, and the electronic degeneracy. Now, one thing which is important, and probably that maybe everyone knows, is that we are in transition metal oxide, so we deal with d orbitals, T2G and EG orbitals. Now, if you have an isolated atom, so forget now about the oxygen octahedra, these orbitals are degenerate. But now in our perovskite structure, we have the oxygen octahedra. And now if you look, this is easy to understand, if you look at the T2G orbitals, you realize that the orbitals are pointing away of the negatively charged oxygen atoms. But if you look at the EG orbitals are pointing towards the oxygen atoms. And so there is a repulsion, this is costing energy, and this is lifting the degeneracy. And this is now the crystal field splitting. So what we find in our perovskite, we find that we have our T2G orbitals, which are here, separated of the EG orbitals by this crystal field splitting, which is large, a few electron volt. Now, one more thing, if you have degenerate energy levels, often the system goes to a structural transition to lift this degeneracy. And this is depending now on the filling of the bud. So this is a nice example here where you see a system with 4 electrons, so D4, high spin. So with our picture, we have our T2G orbitals here, the EG here, high spin. So you put your 3 electrons in the T2G, and you have 1 electron in the EG, degenerate state. The system doesn't like this, and the system goes through a Jahn-Teller distortion. So you distort the octahedra. This is what you see here, and this is what you see here in a crystal. Now, it's quite easy to understand what's happening. You see here that since you distorted the octahedra this way, the Z orbital are further away of the oxygen atoms, and so they go lower in energy. And this is what you see here, and the same for the XZ and YZ orbital. And you see that this way the system is gaining energy. So you will go through this Jahn-Teller distortion. But now, if you have a D5 system, still high spin, 3 spins here, 2 in the EG, this way this Jahn-Teller distortion doesn't help. So the Jahn-Teller distortion will occur for the D4, but not for the D5. And now the important thing is that when you lift the degeneracy, you end up with a system which is half-filled, and you can eventually go to a Mott-insulating state. So as we will see, the nickelates are in a rather similar situation, but they find another way to lift the orbital degeneracy. So let me describe now these rare earth nickelates. So as I said, they are well known for their metal to insulator transition, and this transition is accompanied by a structural transition, a breathing mode. So every other octahedron expands and the other contract. At low temperature, and this was described by Andrea yesterday, they develop a quite complex antiferromagnetic state, which has the peculiarity to develop along the 1-1-1 direction with a 4-unit cell periodicity. And this will be important in a minute. And these materials have been the subject of very, very many studies, and there are millions of papers on nickelates. Obviously, I will not be able to tell you about all this. The structure, as I said, the nickelates are orthorhombic with this particular rotation pattern A minus, B plus, C minus. The phase diagram that you already saw yesterday is shown here. Temperature, tolerance factor, or nickel-oxygen-nickel bond angle. And now you see an important thing. This is the metal to insulator transition as a function of the rare earths that you have in your nickelate. And you see that this metal to insulator transition temperature is related to the level of distortions of the system. So the less distorted nickelate, lanthanum nickelate, is metallic all the way down to low temperature. And now the smaller the rare earths, the larger the distortions, and the higher the metal insulator transition. And this is linked now to our tolerance factor, which is becoming smaller and smaller. The rotations are larger and larger, and the nickel-oxygen nickel bond angle is going smaller. This is a magnetic transition. that now is going this way, and you see that neodymium nickelate and praseodymium nickelate have a joint transition, so you have a metal insulator transition accompanied by the magnetic transition. For the others, it's decoupled. The structure, lanthanum nickelate is a special member of the family. The structure is rhomboidal, A minus, A minus, A minus. The other are orthorhombic in the metallic phase and turn monoclinic in the insulating phase. And this is what I wanted to mention, what I just mentioned before. When you go down in size, you change the nickel-oxygen-nickel bond angle. By doing so, you change, this is what you see here, you change the overlap of the orbitals, you reduce the bandwidth of the system, and the system turns insulating at higher and higher temperature. This can be used in thin films. One can use in thin film strain to change these rotation angles and affect the metal to insulator transition. This is what you see here for neodymium nickelate, resistivity versus temperature, films grown on different substrates, and you see that although the change in rotation pattern is quite complex, you see that you can modify dramatically the metal to insulator transition from here about 150 K to maybe 100, and eventually the films stay metallic all the way down to low temperature. Let me say something about the order of the transition. Andrea mentioned yesterday that neodymium nickelate has a first order metal to insulator transition. This is what you see here. Again, resistivity versus temperature. This is neodymium nickelate, and you see this nice hysteresis that you already saw yesterday. But now if you measure samarium nickelate, neodymium nickelate, maybe it's important to show, neodymium nickelate is here, samarium nickelate is here. When you measure samarium nickelate, you see no hysteresis in the measurement. And it has been proposed or discussed that eventually the reason is that when the two transitions, metal to insulator and magnetic transition, are coupled, like here, or like for neodymium nickelate, the transition is first order, but when they're decoupled, the transition is second order. So we decided to study this, and what we did, we grew some solid solution films between samarium nickelate and neodymium nickelate. So we grew materials like the one you see here. And these solid solutions are shown on this graph. So 3 different samples, 1, 2, 3. These 3 samples display metal to insulator transition. They all display hysteresis. And the question now is, what is the magnetic transition temperature in this system? So what we did, we measured this magnetic transition, and the way you do this, you perform resonance soft X-ray diffraction at the nickel L edge, and you look for the long wavelengths, these 4 unit cell wavelengths of the magnetic order. And this is what you see here. So you have to rotate, if you think about it, you have to turn your sample to access the 111 planes. But if you do this, you see here the intensity as a function of 2 theta, and this peak here is a 1/4, 1/4, 1/4 peak, which is a signature of the magnetic order. And when you see this peak, you can follow now this peak as a function of temperature. You follow its intensity. This is intensity versus temperature, and you see, for instance, here, that this magnetic transition, this Néel transition, is around 200 degrees C. So this is what we did with a series of samples with the goal of checking whether or not the metal insulator transition and the magnetic transitions are coupled. And the measurements are shown here. So these are the 3 different compositions of these solid solutions. The resistance versus temperature and the integrated peak intensity. So for this sample, the 2 transitions are coupled. But what we find that these 2 samples have decoupled Néel and Mi transitions, also still showing hysteresis. So the conclusion of this recent study is that the order of the transition is not linked to the fact that these transitions are coupled or not. And yes, sorry.
Here you're talking about the coupling between magnetic and electronic. But what about the lattice? Because in one
Yes. So you get. The structural transition you're mentioning occurs along with the metal to insulator transition, always. 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 But the point is that people were proposing that if additionally you couple to magnetism, eventually it's second order. But there is something I forgot to mention, and it's good that you asked a question, is that if you look at the hysteresis width, you see that this hysteresis width is going down as you go up and up in temperature. And so it is well possible that, in fact, samarium nickelate is also as a first order transition, but you do not detect the width. Okay, let me discuss. Yeah. No, it's not. It's this is an issue with the measurement of the temperature during the. No. It's not hysteretic. I should say it's a difficult measurement because in Paris where we perform this measurement, the thermometers are quite far. So what we did, we perform resistivity and this intensity measurement at the same time, and the key point is it coupled or not? The details, Yes? I think so, yes. I see. Yeah. That's a good point. It would be much easier than to perform this measurement. Yeah. Here we wanted to follow this because that was a key point to follow magnetism, but there is an issue with thermometry in this experiment. Let me go back. So what Manuel is saying is that if you look at the derivative of this curve, there is a small anomaly, which we didn't search for this anomaly here. I see. Okay. Yeah. Okay. So we should look into this. Yeah. Okay. Let me move now and discuss the electronic structure and the origin of the transition. So in our nickelates, nickel is 3+, D7 low spin. So remembering what we said about the T2G and EG, we are in this situation with full T2G orbitals and one electron in the EG with a degenerate state. As Andrea mentioned yesterday, we can also have a picture where the system is D8L with a ligand hole with the oxygen. And the origin of the transition was discussed in this important paper of Igor Mazin and co-workers. And the origin of the transition is this bond and charge disproportionation. So it's linked to this breathing mode. In this paper, they're saying nature abhors an orbital degeneracy, and the solution is to develop a Jahn-Teller distortion, what I just explained before. But to get this Jahn-Teller distortion, you need narrow bands. And if the bands are too broad, the kinetic energy dominates and the Jahn-Teller instability is suppressed. So the proposition of Igor Mazin and co-workers is that when the on-site repulsion energy is of the order of W and the Hund's coupling J, the system finds another trick to lift the degeneracy. And this trick is to go to this breathing mode. So at high temperature, you have a single octahedra size, but when you transition, you go to this breathing mode, and one of the octahedron becomes larger. This is a long bond, and the other shorter, short bond. And obviously, when you do this, you change the energy of these levels. And in the extreme case, you would transfer the two electrons on one side, lifting the degeneracy. So the picture is a high temperature metallic state, which is here, electronically degenerate, bond proportionate, and you turn into a low T insulating state, non-degenerate, and bond disproportionate. And then the system turns insulating, and some people talk about a site-selective Mott insulating state. To describe the transition, we can use two order parameters, and this will be useful later. The first one is n, the electronic disproportionation, and this is simply the difference in number of electrons on the long bond minus the short bond. So this is the metallic state, 1, 1, so n equals 0, and in the extreme case, in the insulating state, n would be 2. The other order parameter you can use is Q, which is the amplitude of the breathing mode, if you want, defined as the difference in bond lengths. So this Q is also 0 in the metallic phase and finite in the insulating phase. Now, in this low energy picture, where we consider only the nickel EG orbitals, you see that the gain in energy here is, we call it delta S. And we can calculate the energy at which there will be this transition, and this is done in this paper of Alaska Subedi, Oleg Pale, and Antoine Georges. And so what they're doing, they're comparing the situation at high temperature, orthorhombic and equivalent site, to the monoclinic phase with inequivalent sites. And you see here the situation in the monoclinic phase. You have this change in energy, which is delta S. You have the two sides, and you see that if you put one electron on one side and one electron on the other one, the gain, there is no gain in energy, delta S over 2 minus delta S over 2. Now, if you put the two electrons on one side, you gain this delta S over 2, but you pay a price because the electrons are on the same side, and you have the onscoupling J. And so this is giving you a condition to switch. Now, in this paper, they describe in more detail the way they see the transition. And the important thing here is that they consider that going to the breathing mode is costing some energy, some elastic energy. So the way the calculations are performed are the following. So the breathing distortion is costing an elastic energy, typically kq square over 2, where q is our order parameter. And there is a gain in energy because you're lifting the degeneracy, minus gq. So minus gq is our delta S introduced before. And unfortunately, there is a change in notation, but nu is n. So it's n over 2. So what does it mean? It means that you're gaining an energy, an electronic energy, which is proportional to the fraction of electrons which will move to the long bond. And the gain in energy is also proportional to this delta S, which is linked to Q. So the calculation is performed this way. You have the energy of the system. You have the gain in electronic energy, the cost in elastic energy. You minimize this energy with respect to Q, and you find this equation. So 2K over G, okay, constant. This Q, which is our order parameter, is equal to nu of Q, or n of Q, which is highly nonlinear and obtained by DMFT. And this is what is the result that Oleg Pale and co-workers found. This is the electronic disproportionation, so nu or n as a function of Q. And you find the curves which have been obtained. And let's follow, for instance, this curve. K over G equals this 5.3 angstrom minus 1. Now you see that for this curve, if you have a large bandwidth, 2.2, you see that there is only one solution to this equation, which is 0. So the system is metallic. If you take a small W, 1.46, there is only one solution for a finite Q, finite nu or n. This is the insulating state. But what you find that for intermediate bandwidth, like this 183, you find two solutions to this equation, and so it's telling you that you have phase separation. So this result is telling us that the transition is first order. And so this is in line with what I mentioned before. Okay, with this, let me now switch to the second part of the talk where I wanted to show you some of the recent, yes, Claude? No, it's static, so it's really a checkerboard pattern. And you can see it using X-rays. Very difficult to visualize. We try to visualize this as pattern directly, but it's a very small effect. But it's static. Yes? I see what you mean. Yes, but in fact, okay, the U in the system is fixed. And what happens is that the transition, if you want, will take place for a certain gain in energy delta S, which itself is linked to the breathing mode. So it's a very nonlinear relation. So when you change slightly the size of the octahedra, you change quite dramatically your transfer of electrons. And yeah. Yes. Yeah, I think you can do this. Some people have performed calculations where they were they could follow. You know, the rotations change with temperature, and they were looking at this particular phonon to see if it's becoming soft at some temperature, producing the breathing mode. So these calculations have been made. So this is another way to look at this problem. Okay, so let me move now to this part where we have realized different types of superlattices with nickelates, and you will see how the things which have been introduced before are useful. So the first thing we did was to realize heterostructures made with two different nickelates, and we chose samarium nickelate and neodymium nickelate. So these two nickelates have two different metal to insulator transition temperature, but also different distortions. Samarium nickelate is more distorted than neodymium nickelate. And when we started this project, we saw that by making these superlattices at each interface, these distortions have to adapt. And we were wondering what will happen. So what we did, we realized superlattices of these materials. So the materials are grown on lanthanum aluminate, and you make different layers. Each layer has the same thickness. So M unit cell of neodymium nickelate, M unit cell of samarium nickelate, and what you're changing is the wavelength of the system, or the thickness of each layer. Yeah, so 400K for one, 200K for the other one. The Néel transition temperature are nearly the same, but here it's coupled, and here it's decoupled. And the general idea was to say, let's measure the metal to insulator transition of the system and use this information to be able to say something about a possible coupling between the layers. So these layers are grown by off-axis magnetron sputtering. You see here the system. If you have a question, I can answer. The characterization is mainly X-ray diffraction, atomic force microscopy, and scanning transmission electron microscopy. From X-ray diffraction, you can get the wavelengths of the system. You can have an idea of the quality of the structure by looking at these fringes, which are linked to the finite number of diffracting cells. And from AFM, you see the surface. So this is typical characterization. This is the surface of the samples. It's atomically flat, so you have atomically flat terraces with one step height. These steps are linked to the miscut of the substrate. X-ray diffraction shown here shows these fringes, which are a sign of the finite number of cells, and additional peaks that you see here, which are linked to the artificial modulation of the length. And this reciprocal space map is simply showing that the films are coherent. There are no dislocations at interfaces. Scanning transmission electron microscopy shows also, I'll come back to this image a little later, shows also that the layers are very well defined. So let's look at the transport property. I will come back to the characterization a little later. So let's look at the transport properties. This is resistivity versus temperature for an entire series of superlattices with different thicknesses of each layers. And what you get is finally something which is quite reasonable. If you look here, this is a 15 unit cell sample, so quite thick layers. And if the layers are quite thick, you imagine that the behavior will be the one of samarium nickelate and neodymium nickelate. And in fact, this is what you see. You see a first transition here. The samarium nickelate layers are becoming insulating, and at lower temperature, the neodymium nickelate layers are becoming insulating. But now, when you reduce the wavelengths, you start to see that these two transitions come closer, and at some critical wavelengths, you observe only a single transition. And this is what you see on this slide. This is temperature as a function of the superlattice wavelengths. And you see that for short wavelengths, below this critical wavelengths, which is about 16, you see that the sample is entirely metallic and turn entirely insulating at this transition. But if you have thicker layers, you have a metallic state. You have a state where one of the material is insulating, the other one is metallic, and finally they're both insulating. And when we saw this at first, we thought, okay, maybe this is simply this coupling of distortions. But we were a bit surprised by the size of this critical wavelength, 16 unit cell. So we decided to investigate what is the origin of the coupling. But before to show you this, let me tell you that we use a beautiful STEM analysis to make sure that what we were seeing in this diagram here was correct. So what we did, we selected two samples, scanning transmission electron microscopy analysis at room temperature. So we took two samples because it will be measured at room temperature. One which is here, a 5 unit cell, which should be where both materials should be metallic, and one here, 30 unit cell, samarium nickelate should be insulating, neodymium nickelate should be metallic. And then we perform yields measurement at nearly at the atomic scale, so it's a local X-ray absorption spectroscopy measurement, and you see the normalized intensity here as a function of energy for the 35.5. And what happens, and I think Andrea mentioned this very briefly yesterday, there is a small subtlety in the spectra here. This is what you see here. And you can differentiate between an insulating and a metallic state by looking at the shape which is here. So we use this contrast in a color map, and you see here for the 30 unit cell, this is now the composition, and this is this class analysis, so that you see that the two layers have a different behaviors. The neodymium is metallic, the other one is insulating, but when you go to the 5.5, you have a uniform composition, which shows that at the atomic scale you can verify that both layers are indeed metallic. So now, what is the origin of this coupling? First thing we wanted to rule out is intermixing, because obviously if you have a lot of intermixing, at some point you have a solid solution, and you have a single transition. But what we saw here is through the scanning transmission electron microscopy, again it's a 5 unit cell, there is essentially no intermixing in the system with extremely abrupt interfaces, as you can see here. The second thing, we thought it's probably linked to now to our distortions, which are different in two materials, and these distortions have to couple at interfaces. So we performed advanced scanning transmission electron microscopy and DFT calculations, and again the answer was very clear, and in fact in line with what we know from other work. When you go from one material, this is now the angle, the nickel oxygen nickel bond angle as a function of the depths in the superlattice, you see that very rapidly you go from one value to the other one, and both the measurements and DFT calculations are telling us the same thing. So it's not a coupling of the distortion. So what is the reason for this coupling? We believe that the reason is the cost of having a metal insulator phase boundary. And this is linked now to the behavior of the order parameter. So this is our n order parameter that I introduced before. And you realize immediately that, okay, if both layers are metallic, n is 0 everywhere. If both layers are insulating, n might be slightly different, but it's more or less constant. But now if you have a metallic and insulating interface, your order parameter has to go from 0 in the metallic state to a finite value in the insulating state. And now if you develop you do an expansion of the energy, you write something like this with n square, n fourth, and n sixth term. But now if your order parameter vary in space, you have to introduce a term which is proportional to gradient of this order parameter square. And this is a term which is written here. And so this is simply saying that bending the order parameter is costing energy. And so we believe that this phase boundary cost is what is controlling the coupling. And you can write it as gradient n square or gradient q square. Yes? Okay. We've been trying to go in this direction, because here what we do, in some sense, it's kind of obvious. If you know the critical wave, you see, for a given energy, there will be a critical wavelength, because the denser the interface density, if you have too many interfaces, you will not allow for this mixed state. So here we use the lambda c as a fitting parameter, so we are not really calculating this. But what we've been trying to do, but I will not show this, is to change the parameters, because you have some equations that you can derive here, and you have some predictions. So for instance, if you're changing slightly the metal insulator transition temperature of one of the material, you know how these parameters should evolve. But from the data, we could not extract directly the. Yeah. I see. No. But we could do this too. Yeah. Yeah. Yes. Yeah. And this is due to electrostatic interactions. There's variation. I'll come back to your point just later. Okay, so we could fit the data using this model. And now let me show you in the 5 or 7 last minutes a few more things. The first thing we were thinking that it would be nice to try tuning this coupling. So how to tune this coupling? We decided to insert something between these layers to try to see if we could modify this coupling. And the thing the idea we had was simply, since we use lanthanum aluminate as a substrate, was to add in between the layers of samarium and neodymium a very thin layer of lanthanum aluminate, a simple insulator. And so the experiment. Yes, sorry.
There is a big difference.
No, it's the same. Same TMI. Okay. What I'm not sure. What I'm trying to say is that if you're here, this TJ, this joint transition temperature, as the value is the one of the solid solution, but only there. But here it's homogeneous, if you want, because it's fully metallic going to fully insulating. So 3D in some sense. It will be different just after when we put this aluminum, lanthanum aluminate spacing layers. Okay, so what we tried to insert this lanthanum aluminate layers, and the way to go is to select a wavelength which is here in this coupled region. So we chose 6 unit cells. So 6, in principle, you have a unique transition, and we put 1, 2, 3, 4 layers of lanthanum aluminate. So if you do this, okay, samples have been realized, have been characterized. There is a small thing I wanted to mention, but I'm not sure I have a lot of time. But since I explained, these measurements of GPA allowing you to determine the direction of the long axis, there is a surprise with this lanthanum aluminate. The entire structure, the entire orthorhombic structure is flipping, and this is linked to the structure of lanthanum aluminate, which is rhomboidal, but I'm not sure I have the time to discuss this. So let's look at the result very briefly. This is now the 6 unit cell samarium nickelate, neodymium nickelate, a single transition. And then it's very simple. As soon as you put 1 unit cell of lanthanum aluminate, it's completely decoupled. So 1 unit cell of lanthanum aluminate is producing the same effects at 2, 3, or 4. You see 1 transition at high temperature and 1 transition at low temperature. So the system is now decoupled. You see this here. This is now the temperature, the number of unit cell, and you see this transition here, and this is the sample without lanthanum aluminate. We also did this with 4 unit cell of neodymium nickelate with the same result. And now the interesting thing is that this experiment are telling us that our critical wavelength, which was 16, is now pushed to 12 and even pushed to 8. So the fact to put lanthanum aluminate, the critical wavelength is going down. But if the critical wavelength is going down, it means that the phase boundary energy is going down. And in our model, it means that the gradient of n is going down. And so the picture, and I should also say that the critical temperature of this very thin layers are very similar to the one of thick ones. So our picture is that probably what happens is that our order parameter n, which is not defined in lanthanum aluminate, because lanthanum aluminate has no D band, is probably more or less constant. And there is no bending, and if there is no bending, there is no cost of due to this phase boundary. But now, if we think a little more, we have our other parameter, Q, and Q is a structural parameter, which is linking the different atoms. So Q cannot be discontinuous. Q has to be continuous. And there are calculations in a very similar system, neodymium nickelate, neodymium aluminate, which shows that the distortions go very quickly to 0 in lanthanum aluminate, but do penetrate a little bit in lanthanum aluminate. And so our picture is that probably in the system, the n order parameter has some value and it is not bending very much, whereas the Q order parameter is doing this. But this is telling us something. This is telling us that n is the dominant order parameter for this coupling, because if it would be Q, we would have a very large cost. So n is probably the leading order parameter. And let me end by showing you one more experiment which has been performed recently. We saw that if this EB, this phase boundary cost, is there, eventually we could use this phase boundary cost to turn a metal into an insulator. So how to do this? We go back to our phase diagram, and a simple choice at first would be to take lanthanum nickelate, which is metallic, and maybe combine lanthanum nickelate with samarium nickelate. But lanthanum nickelate is rhombohedral, so we have another structure, and we thought maybe it will complicate the thing. And also lanthanum nickelate is a very good very metallic, so maybe it's not the best choice. So what we decided to do is to move a little bit in the phase diagram and try to find a material which is orthorhombic, which is metallic, but which is a bit closer to an insulating state. And so we made a solid solution of lanthanum nickelate and neodymium nickelate. And there we profit of some previous work in the group by Jennifer Fowley, who studied solid solution of neodymium lanthanum nickelate. And you see here Raman measurements which allow the structure to be determined. And we know from these measurements that up to this point we are in the orthorhombic phase, and we turn rhombohedral here. And there is a part of this phase diagram, the pink region here, where the system is orthorhombic and metallic, and we decided to target this. So we grew these neodymium 07, lanthanum 03, nickel 03 films, fully characterized them. We checked here using alpha order peak analysis, but I have no time to discuss this, that the films are orthorhombic. We have this confirmation by transmission electron microscopy. We also confirm the composition, and importantly for this experiment, the films are metallic. So what we did, we grew we grew these superlattices now with samarium nickelate and the solid solution, and we want to fill again this phase diagram. Now, if you think about it, if you have thick layers, probably these layers will be decoupled, and since one of the material is metallic, it should be probably metallic all the way down to low temperature. Here, for the very thin layers, it's always difficult to know what will happen. So the interesting region here is the middle region here, where we hope to have insulating solid solution layer in the superlattice, but to have a metallic single layer. So let me show you the results. Again, the characterization. This is a thick superlattice, resistivity versus temperature. And you see that it's metallic. A small bump here, the samarium nickelate layers are turning insulating, and it's metallic all the way. 8-8, now interesting, we see two transitions. So the solid solution is insulating in the superlattice, but metallic with a small upturn. But if you look very low resistivity as a single layer, 6-6 again, two transition, still metallic. And so we believe that indeed here, this phase boundary cost has pushed these metallic layers to be insulating. And you see the full series here, and it's been analyzed using the same theory. So if we compare the two results, for the first neodymium nickelate, samarium nickelate, the interesting region was the region here with the coupled transitions. Here for these solid solutions, it's more this middle region where we see two transitions as the single layers are still metallic. And let me just end by saying that obviously there are many more things to do and exciting developments. I don't think we had any talk at this point in the conference, but there is a lot of excitement these days about the oxygen control in oxide structures. And I think many of you know that one can go from the 113 phase that I've been discussing a lot here to the 112 infinite layer phase. Beautiful work by Denver Lee here in the group of Harold Wang at Stanford, showing that these infinite layer nickelates are superconducting. We're working on this. We now have a good phase. Manuel is working also on this. So many people are moving in this direction, and this is really an exciting and I really hope that we will have soon results and that I will be able to show you this. So to end, let me mention the persons who did the work. Regarding the growth, the transport measurements, Lucia Barbaro, PhD student in Geneva. She has done a lot of the work you've seen. And previously, Claribel Dominguez worked on the samarium nickelate, neodymium nickelate superlattices. The beautiful transmission electron microscopy work was performed by Vivian Su. And Bernard Mundet previously in the group of Duncan Alexander at EPFL, and two former members, very important, Jennifer Fowley, who is now at Northwestern, and Marta Gibert, who is at TU Vienna, and collaborations with CCQ, Alex Georgescu and Demilis Antoine Georges, and with a group of Philippe Gosset. And thank you very much for your attention. Thank you.